Okay, here's section 7.2, and now we want to rotate around arbitrary lines. Now they aren't real arbitrary. They're still going to be parallel to either the x or the y axis. But so let's take something like what was I doing? Y equal x squared. Okay, so here's x squared. And, you know, before we say rotate it around the x-axis, but now suppose I want to take this same curve and I say, well, let's rotate it instead of around the x-axis. How about y equals 1? And, you know, so we're taking maybe from 0 to 1. Well, we need to think about what that shape looks like. And you think about the image that's symmetric across that y equal 1 line. And so if I rotate this thing now, right, this place where it crossed oh, well, that's 1. So suppose I go out here to 2. Well, let's not do that yet. Let's just go to 1 first, and then we'll toss in the more complicated. So I want to rotate from 0 to 1 around this thing. Well, it's still the same idea because my axis, well, my axis of rotation, the line y equal 1, is that rotational axis. Then I'm going to slice perpendicular to it. So I'm going to cut things up on the x-axis again. And so I will have an integral from 0 to 1. And then with those slicings, now I need to come up with the radius. But see, now the radius is that. And so as I look at that, the radius is actually, the radius is 1 minus x squared. And so I need pi times that radius, so 1 minus x squared, and then dx. Okay, so it's always pi r squared h. It's just trying to figure out what what the radius is, and then h is typically a dx or a dy. Well, we're slicing this way, and so we do that. And well, okay, if I want this integral, I have pi times, and I just multiply that out. I get 1 minus 2 x squared plus x to the 4th dx. And so that's pi times x minus 2x cubed over 3 plus x to the 5th over 5 from 0 to 1. And nicely, the 0 doesn't matter, makes everything 0. And so I get pi times 1 minus 2/3 plus 1/5. And so that's, well, let's see, I guess I need to go to 15ths. So that's pi times 15 over 15 minus 10 over 15 plus 3 over 15. And so that is 15 minus 10 is 5, plus 3 is 8, so 8 pi over 15. Okay, and you know, so again, the point is it's always just pi r squared h every single time if we're making a disk. We just need to figure out the r squared. We need to figure out the h. Okay, Now, so to build on this, now I'll go out to 2. So there's 1, there's 2, and again, suppose I want to rotate about y equal 1. Well, when I do that, I'll get this figure that looks, I don't know, sort of like an hourglass or something like that. And so to find that volume, again, since I'm rotating about y equal 1, I'll cut it up perpendicular to the x-axis because the y equal 1 is parallel to the x-axis. So I cut it up that way. And now, though, you see my radius is going to be a little bit different on each side. So over here, well, we already did that. That's 1 minus x squared. Okay, but on this side, that distance to get that, I need actually x squared minus 1 over here. Okay, so, I've got x squared up here, and so to find that distance, I need to take my x squared value minus 1, whereas back here it was 1 minus x squared. So now, to do this problem, I will have an integral from 0 to 1 of pi times 1 minus x squared squared dx, and then plus an integral from 1 to 2 of pi times x squared minus 1 squared. Now, here's the nifty part. Because we're squaring this, we actually get the same integrand in both cases. So, so it turns out, if I hadn't really thought about it and just said, oh yeah, it's the function x squared, I want to take 1 minus that, and so forth, and just did it, it would have worked out okay. Now, why is it working out okay? Well, because in the end, what we are doing is we're taking the difference between our curve here and 1, but then we square it. So it actually doesn't matter if we find that difference between them in the positive, which is what we did here, or if we had it go negative, which if we hadn't changed the x squared minus 1, we would have had 1 minus x squared. That would have been a negative number. But we end up squaring it. So in a practical sense, it didn't matter. Okay, but you want to be careful of those things because maybe it will matter in a different application. But in both of these, we'll just get that same solution here as far as the inside squared. Now, I already know this first integral is 8 pi over 15, so I'm just going to go with that. And then plus, here, again, we have our integral from 1 to 2 of pi, and I can write it again in the order I had it before, the 1 minus 2x squared plus x to the 4th dx. And so this is 8 pi over 15 plus pi times, and just as before, we have x minus 2/3 x cubed plus x to the 5th over 5. But this time it's from 1 to 2. And now 1, actually, I know the answer to that. It's 8 pi over 15. So really, I only have to worry about the 2 part. So this is going to be pi times, putting the 2 in, I get 2, 2 cubed is 8, so then minus 16 over 3, and 2 to the 5th is 32, so plus 32 over 5. Okay, so I would have that, and then minus putting the 1 in, but I know if I put the 1 in, I get 8 over 15 to make that 8 pi over 15. And so what I see is that the answer is just going to be that part, because 8 pi over 15 minus 8 pi over 15 is 0. And so my answer is, again, over 15. So 30 over 15 for the 2, minus 5 times 16 is 80 over 15. And then 3 times 32 is 96 over 15 pi. And so this is a minus 50, so plus 46. So 46 over 15 pi. And that would be the volume of this more hourglassy looking thing. Okay, so 46 over 15 pi. All right, and so this is the idea of rotating about some axis other than the x-axis or the y-axis.